6.3 volume by slicing. In this case, we're now going to take what we know about area under a curve or between two curves, and we're going to go ahead and try to do volume. So the first thing we're going to work with is if we take the XY plane, and sometimes it's slightly easier to see it if we tilt it. We take what we have here and we're going to try to see if I can try it, like lay it flat. We're going to tilt it like that. So sometimes we can draw it like this one here. And we're going to do one right now that is a volume of a shape given a function, and it's flat on this like paper. If we were just taking this XY plane and laid it on a table, and then I drew a graph, but then I had something that came out in a 3D shape. So like say it was half circles. And it was a bunch of these half circles between the x-axis and the function. And then it creates a 3D shape that comes out. It's flat. It might have a shape like this at the end. And we can have a 3D shape like that. So this is something we call a mathematician's paperweight. It's basically something that would lay flat on a table, but it has a volume to it. So these are the first examples we're going to be walking through with. So we have here that we're going to use some kind of area. If I was to take this slice, just if I take, for example, this half slice and I move it and I flatten it back out, getting a cross view of that shape, it should be the area of half of a circle or a semicircle. So we know that the area of this should be 1/2 of pi r squared. So if we take these slices and we sum them up, so we're going to integrate and say we're going to go from 0 to, let's say it's 4. I need to go from the x-axis to my function, and that's my diameter. So then I could then need to find r, and then I'm going to go ahead and I'm going to sum up these areas and have volume. So now what we do is we call this, general slicing method for volume. Suppose a solid and it goes from A to B. We take the cross section of the solid perpendicular to the x-axis and in a given area of a function that is integrable. And then we say the volume of the solid is, if you notice, volume of the integration from A to B of the area now. So for example, let's do number 7. So for number 7, they tell us we want to do a mathematician's paperweight given the functions y equals x squared and y equals 2 minus x squared. And it says for areas where the areas perpendicular to the x-axis that are going to be squares coming off of this. So we know the area of a square is side squared. And we're going to use that principle. So if I want to try to do a quick sketch, and I'm going to do it flat on, we have here's x squared. And then if I draw the 2 minus x squared, I get this shape. So I'm going to have, and I'm going to try to draw it this way, squares coming up off of this shape. So even for here, it's going to be a square coming up off this shape. But notice I have not between the x-axis, I have it between two functions. We know how to work with that. We know that the side length of this square, we need to find s, is going to be the upper minus the lower function. So right now I have the upper function minus the lower function, or this should be equal to this. This is my S when I go to plug it into the formula. So for area. So then the next thing I know is I need to find out A to B. I need to know where these two functions cross. So to find A and B, I'm going to set them equal. And then when I go ahead and I move everything over, and then I solve for x, I should get x is equal to a positive and negative 1. So they're saying this is a negative 1 and this point is a positive 1 on our graph. So we now have our A to B. We know what the side is when I go to plug in area. And remember, we're going to integrate area. So going ahead and finding my volume now, I'm setting up my bounds. I'm setting up my side. Area for this we said was squares. Oops, let me rewrite that. So if this was S, my area is S squared dx. So now I'm going to go ahead and you can just take the antiderivative, calculate it. You know with this squared, you want to, if you're doing it by hand, expand it out so that I really have 4 minus 8x squared plus 4x to the fourth dx. Finding my antiderivative and evaluating it at my bounds, I should get 64/15. So we know how to do our antiderivatives and evaluating using fundamental theorem of calculus part 2. So we get this volume of this mathematician's paperweight. So let's do another one more. Given this function, and it says here that we can try to do this without a graph, but we're given this function and it's the shape that's coming perpendicular to the x-axis are isosceles triangles. So remember, this is a triangle. They're saying where the one leg is perpendicular and on the surface of the xy plane. So it's perpendicular to the x-axis and is going on the xy plane. In this case then, this shape should have a bunch of these triangles like this along its shape. So we know then we're going to have that situation to deal with. So we have to figure out what is the area of the isosceles triangle. It should be 1/2 base times height. But the key thing on this was that the base and the height, because it was an isosceles triangle with one of the legs down on the base and the height are equal. So if that's the case, I really could use basically b squared. Makes it a lot easier to go ahead and then calculate, and I don't have a height to try to go find. So then when I need to find my bounds, and if I go ahead and find my bounds, I'm basically trying to find when the square root of cosine x is going to be equal to 0, where it's going to be crossing the x-axis. And solving for it, I get that x should be a positive and negative pi over 2. Because remember, you would square both sides, and then the question becomes, where does x equal 0, or where does cosine equal 0 at a positive and negative pi over 2. So there's our bounds. And then I'm going to go ahead and just do our integration here. So we're going to go from negative pi over 2 to pi over 2. We have that the area of these triangles 1/2 b squared. Our b is the function then, because we're really subtracting it from the x-axis. So that's the upper function. So we have the square root of cosine x quantity squared. So b is the square root of cosine x. And then I'm going to go ahead and we're going to integrate this. And if I wanted to simplify it, remember the 1/2 can come out as a coefficient. And then I have the square root that is being squared, and I just get cosine x dx. Much easier to find the antiderivative of this. Should be 1/2 sine x from negative pi over 2 to pi over 2. And if we go ahead and use FTC2, we see that it should have a volume of 1. Whatever units cubed, they of course don't give us any units. So moving on, We want to do the disk method. So what this means is now I'm no longer a paperweight. I'm no longer flat on the XY. What we're doing now is we're going to be rotating some kind of shape. So to start with, what if I have some shape that was like this? And this I can find the area for. But what we're going to do now is rotate this shape. In this case, we're going to go ahead and basically have a circle. Oops, and I kind of went off my axis a little bit. But basically, this shape that was now spinning around, and I have these different, and I could almost do cylinders. If I wanted to, I could say, well, I could find this cylinder, and then the next cylinder, and then the next cylinder. And then we're going to, it's still that slicing method that we want to sum up. And we want to get infinitesimally small little heights or widths to our cylinders. And we know the area that we could use for this. In the cross view then, if I was to take this cylinder and lay it flat, it's just a circle. So this is where we're going to use pi, the area of a circle is pi r squared. And then it's going to turn out that r, or our radius, has to be from the x-axis, to back to the function. So we're going to go from the x-axis back to the function. So we're going to use this for our equation then. So that's why you see the volume here is always going to be, using the disk method, when we start rotating, pi, the function squared, dx. Remember, dx is our widths of our slices. So then, knowing this then, we want to try to do some examples. Let's do number 19. For number 19, we're given that we have the function y equals e to the negative x, y equals 0, x equals 0, and x equals ln of 4. So this problem says, in number 19, that we want to find the volume for this region R bounded by the following curves. Use the disk method to find the volume by the solid generated around the x-axis. So everything we've been doing right now has been in respect to x-axis. So a lot of times we denote it with a little arrow that shows which axis we're going to be rotating around. So they're saying now, given all this information, find the volume by the disk method rotating around the x-axis. You could draw this in a quick sketch. You don't have to. Just roughly, there's y equals e to the negative x. It says we're going to be bounded by the y-axis, the x-axis, and we're going to stop at when x is equal to ln 4, which is some value. So they're now saying, okay, this is the area that we are now rotating around the x-axis. So that's creating some kind of shape that would have, if we were to lay it up on its side, maybe something like that of a shape. So we want to find this volume. So we're going to go ahead using what we know that we have to find the bounds. Well, it looks like our bounds are going to be from 0 to ln 4. And then we said that the formula will always be pi, and then the function f of x squared dx. So in this case, and always with the disk method, or even the washer when we get to it, pi is a constant. It can almost always automatically come out as a coefficient. So we can go ahead and just factor that out like that. And then I'm going to simplify power rule for this and get negative e to the negative 2x dx. And then we can find the antiderivative of this. So that we have, if we go ahead and do our antiderivative, we should have 15 pi over 32 for our volume. Let's go ahead and try number 20. In this one, we want to find the volume. It's going to roughly look like this, where y equals cosine x, and we're going to be between y equals 0 and x. Oops, x equals 0 it should be. So let me double check that on our problem. Y equals that. And then recall, if I see here, because I'm going to be squaring this, the book gives us a hint. Remember that cosine squared can be replaced with a trig identity that happens to be 1/2 of 1, plus cosine of 2x. So I have a lot easier way of integrating if I remember that fact. So if we're going to go ahead, we just need to make sure we know where our bounds are, which they gave to us. Will be from 0 to where cosine x would hit the graph. So you'd have to find that, and that would be at pi over 2. So there's our bounds. And then we're going to go pi, which I'll pull out, and then we're going to have cosine squared of x dx. And then we said if we use this identity substitution, we could replace it with 1/2. That can be factored out. And then I have 1 plus cosine of 2x dx. This becomes a much easier problem to integrate. And if you have no problem otherwise, go ahead. But from here, we could see then finding the antiderivative should be x plus sine 2x divided by that 2, and then evaluating at 0 and pi over 2. And when we go ahead and do our FTC2, we should get pi squared divided by 4 as our volume for this problem. All right, so now moving on, we're going to use the washer method. The washer method actually turns out that we've got a hole in something. So if we took a cross view, we would have an outer circle, some thickness, and then a hole. So if this is the case, some books teach us that we'll call this a radius of r from the center, and then some say, okay, use this as a little r. We're going to have to do what we know of the area between two curves. It's always going to be the outer minus the inner function, but we're still applying this area of a circle, and we're just subtracting the two areas. So if I was to do the big area, it should be pi capital R squared. And if I was to do the area of the small or lowercase r, it should be pi r squared. So the big thing about when we find the volume of this, we're going to do the outer minus the inner. So if we were to take pi capital R squared minus pi little r squared for our area of the washer, I can factor out the pi. And then this is our equation for we're going to use in here for this one. They used it in terms of function. F of x would be the outer function, g of x is the inner function, but it's still the same thing. The important part of this is remember this that we have written below is not the same thing as this. It is not the differences in the radiuses squared. It's using the two area formulas for the circles and subtracting them. So we're going to use this. We could say dx, or in this case, if we're leaving it with r, dr, and we can go from a to b. So they have it with the function notation. I just showed you a little bit with using the idea of a radius. So that when we go to draw a picture, and for example, we're going to be doing problem 28, and our function is actually going to look like this. And it's this area that is now going to rotate around the x-axis. So now when I rotate it, I'm definitely going to get something that looks a little bit like I have a solid. This has a thickness, but I have a hole in the middle, hence the washer. So this void under this is the hole in our washer as we go ahead and rotate and spin this. So when we go to do this, set this up, you need to find where they intersect. So for 28, they give us that the function is y equals x and y equals the fourth root of x. So we're going to want to go ahead and find where these two intersect, and we should get x to the fourth minus x equals 0, and we get x then should be 0 and 1. And then we know we can have our bounds. We know the volume is going to be pi times the integration from 0 to 1. And then we know we're going to take the outside function or the curve, which is the fourth root of x. I'm sorry. Fourth root of x minus, I'm sorry, that's what I'm missing here is the squared times the x squared, and then the entire thing times dx. So going ahead and taking the fourth root of x squared leaves us with the square root of x minus x squared dx. And then we can go ahead and put that in exponential form, find our antiderivative, and then we should get down that our volume is pi over 3.